So the system we are going to consider today is the harmonic oscillator. You can consider it to be the most important system in all of physics, and certainly in quantum physics, but I would say almost all of physics. So let me, because a lot of people may not have studied much physics, so let me just say a few words about it. So it's, if you have a force which is proportional to the distance and opposite direction to the distance. So that means if I have, this is my starting point. Let's say this is the origin. Just wait a minute. I don't know what's going on with my. Um, could this be because of a magnet around? So you have, let's say, this is your origin, and this is the positive direction of x. The more your particle is away from this origin, the more is the force, and it's directed towards the origin. So that your equations of motions are, so F is minus kx, and equations of motion is the following. Mx double dot is minus kx. And so that means that the acceleration is directed inwards. If you are here on this side of origin, it's directed this way. If you are on the right hand side, it's again directed inwards. So you pull the particle and the force pulls you back. So you can approximate a spring. A spring's force is of this kind. You pull it outwards and the force pulls you in, and the more you pull it, the harder is the force which is pulling on the particle. It doesn't matter which way you are pulling it. It's always pulling it inwards, and it's linearly increasing. As you pull the spring more, there is more force. So that this is a kind of a system is called the simple harmonic oscillator. And the solution of this is very easy. This is the equation, and its solution, if I call k over m as omega square, it's a positive number, k over m, k is a positive constant. Then this is the equation, and its solution is easy to write. If I want, I can write the complex solutions, but since position is supposed to be a real number, positions are real numbers, so I would rather write it using the real solutions. So I can write it using a combination of cos and sine, or I can absorb the sine into this phase and write this solution. So it's a second order differential equation. So solution has two constants. So wait, I have to take this call. Just wait a second. So you have this solution, and what this solution is describing for you is that if I plot it, and I'm plotting omega t's here, pi by 2, pi, 3 pi by 2, and 2 pi. So if I choose phi to be 0, for example, it doesn't matter, but just as an example, let me choose phi to be 0. Then the solution goes like this. Well, it's supposed to be go as high as this. Like this. And I can plot the speed. So if I take one derivative, that gives me the speed. And it's just the sine graph, but it's inverted. So it looks like this. So what these two graphs are telling me, so x starts with the value a. So a is the amount by which I have pulled the spring. So x is equal to a at t is equal to 0. So when I release it, now the force is acting on it, and the speed starts with 0, and the speed is directed inwards because it's a negative sign. And by the time it reaches the middle, this ball, then the speed has reached its maximum magnitude. And as you cross this line, the speed is still negative. Uh, so uh, so you cross this line, and then the speed is still directed in this direction, but it's reducing. So it slows down, and when the speed becomes 0 over here at omega t is equal to pi, then the position, this line is position and this line is speed, then the position has attained its maximum value in the negative direction on the other side. So it stops here and then starts accelerating in this direction because now the position is decreasing, going towards 0, and the speed is increasing. This red line is increasing. So again, when it crosses the middle, the speed is maximum. So it stops momentarily at the ends, and it has maximum speed in the middle, and it's just oscillating like this. And since this oscillation is described by a cosine function, cosine or sine doesn't matter. So that's why you call it a harmonic oscillator. Now, to describe this oscillator quantum mechanically, we will have to replace the force by potential. And since force is minus kx, I can easily guess what the potential has to be. It would be half kx square because force is minus dv over dx. So it will give me 2 over 2 kx minus kx. But I said that I'm calling k over m as omega square. So that means k is m omega square. Therefore, the potential is half m omega square x square. So this potential is like the standard way to write a simple harmonic oscillator potential. Any potential which is of this kind, this alpha is positive, and you have an x square. That's a simple harmonic potential. It's just customary to write this constant appearing like this, because once you write it like this, then you immediately know that this omega, which is appearing in this constant in this p factor, is going to be the frequency, angular frequency of the oscillation. and m is the mass of the particle. Because you can see that depending on k, you have different frequencies. Once you fix this k in this force, your frequency is fixed. All you can do is change this a and phi. You can changing a means pulling it, giving it a a larger maximum distance. Because from this graph you can see a just corresponds to the amount by which you have pulled, or the distance it covers in its oscillations. So oscillations can be small, oscillations can be larger, any oscillations can take any size, doesn't matter, all are allowed. But no matter what is the amplitude of the oscillation, the frequency is always same, omega. That's fixed by that constant k. So frequency of oscillation is a characteristic of potential or force. Depending on what potential, what are uh, these constants in front of the potential, inside the potential, your frequency is fixed. It's not a characteristic of the solution. So, and why is this potential so important in physics? Well, if you are describing any particle which is trapped, your potential will look like something like that. What does this mean? This means if I leave a particle here, for example, particle, if I leave here, that means that there will be a force in this direction. So it will try to roll down. And if I leave it anywhere over here, it will try to roll down. And you expect that it will go like that, and depending on what is its energy, it will oscillate like this. So all trapping potentials, all potentials which describe bound states. So if you are trying to describe any system which is bound, so it could be an atom, some electron inside the atom, even in classically speaking, some things which are held together through various springs or through any metal, as long as they are not flying away, there are forces which are keeping them confined, then it will take some form of a potential like that. So any potential like that, if you look at it near its equilibrium position. So this is the equilibrium position. If you leave the particle here, it is stable. There are no forces over here because dv over dx at this point is 0. So the force is 0. So at the valley of the potential, there are no forces, and that's the equilibrium position. If you disturb the particle a little over here from its equilibrium position, then you can describe the potential near the equilibrium position is given by, I can just Taylor expand it. I can call this position, doesn't matter what you call, but I can give it a coordinate 0. So then this would be V of 0 plus X V dash of 0 plus X square V double dash of 0 plus X cube V triple dash of 0, and so on. Now, since we are expanding around the equilibrium, so this is going to be 0. And a constant added to potential, as we discussed last time as well, doesn't matter because it doesn't enter the force. When you compute the force, the constant term drops out. So the most important term over here, and since you are assuming that you are near the potential, so these terms will not be important. This is the most important term. So you can approximate it by, this is a constant, times x square. So all potentials, at least confining potentials, look like harmonic oscillator near the equilibrium. So to first order, you can describe all oscillations through simple harmonic oscillators. That's why they can approximate a lot of systems, and they appear at a lot many places in physics. Now, taking this system, so this was just some classical statements about it. We want to solve the quantum mechanical problem. So our Hamiltonian is, as usual, the kinetic energy plus the potential, which I'm writing like this. And these are the operators. P hat is the momentum operator, and X hat is the position operator. And you want to solve this equation. This is always our strategy. We need the eigenenergy spectrum because it tells us the full time evolution. And also, knowing the energy itself is one of the most important physical uh, statement you can make about any system. That what are the possible energies that the system can exist in. Now, what I'm going to do, I'm going to try to find out the spectrum or solve this eigenvalue problem. So the strategy which I'm going to use, I have something like this: p square plus x square. Or let's write it this way: x square plus p square. There are some constants involved. I'm just making an argument. I can absorb them, the constants, in some redefinition. If I can write this thing like this. So this will give me x square plus p square, but also things like this. If they were classical, they were just variables, then this term will cancel, but now it doesn't cancel. Rather, x p minus px is just this commutator, which I know is iota h bar. So this thing becomes something like that: x square plus p square plus h bar. And this is just the Hamiltonian. So the Hamiltonian becomes this operator, let's call it A, and this operator, this is actually the dagger of it, plus some constant, and that's equal to h. So I have kind of factorized the sum of squares. Although you do get these cross terms which quantum mechanically do not vanish because they are operators, but their commutation relation is just adding a constant. Now, if using the properties of these individual operators, I can hope to find the spectrum of this operator H, because it's going to be just the spectrum of this guy plus added some kind a constant. So this was just hand waving and just an invitation of why I'm doing what I'm just gonna do right now. So let's kind of follow this strategy, but more carefully. So this is the my Hamiltonian. This is the operator. I have this relation. So I know that if I divide by this under root h bar, democratically distribute them in those two, this is going to be iota. So this is the kind of thing which I want here. And I have these two m's, so I'm just gonna redefine things. So let me take this h bar out because I have a square here. And just let's take this 1 omega out. If I pull them out, I get h bar plus omega over 2h bar x hat square. Now, using these constants, I'm just going to define those kinds of a's. So define a as m omega. So just taking this out. Taking this into account, x hat. So take this whole thing and think of it as an x.
सर
Huh?
ये ऊपर ए डैगर के साथ माइनस एच कट नहीं आएगा क्योंकि हम लेफ्ट हैंड साइड पे लेके गए हैं.
I don't care. It was just very, very hand waving. So
it is like कोई फर्क नहीं पड़ेगा.
Parega, this is not a calculation. This was just very, very hand waving. I was just explaining a concept that why I'm going to do what I'm doing now. So I wasn't careful about any sign or any constants. So now I define this. So that's what I'm going to do. So that's what I said I'm going to do over here. Split this x squared plus p squared into x plus iota p and x minus iota p. So that's what I'm doing here. Take this, the square root of this, plus iota square root of this guy. And no principle is involved. I'm just trying to factor them and see what happens. No mathematical principle is involved. I'm just trying to do some algebra and see what happens. So this is a new operator which I have defined. And notice that this is not Hermitian, because if I take the Hermitian conjugate, x and p are Hermitian. These are real numbers, so they don't change. But iota changes sign under Hermitian conjugation. So I get, when I replace plus with minus, I get the Hermitian conjugate of A. So A and A dagger are not Hermitian, they are Hermitian conjugates of each other. But because of this minus sign, I'll do it probably later. I can write x in terms of A and A dagger. If I just add these two equations, I get the expression for x in terms of A and A dagger. And if I subtract these, I get an expression for p in terms of A and A dagger. That will be useful much later. But what is more interesting to note right now, because, yeah, so I can just compute this commutator. So what is this commutator? I'll have this commutator with this. That's going to be 0, obviously, because every operator commutes with itself. Similarly, this is going to be 0. So I only need the cross terms. So when I do this cross term, I get minus iota m omega halves cancel. Let me write it for now. And I get x hat p hat. But when I do the commutator, then I'm writing the same term, but with the order of p and x replaced and a negative sign. So that gives me x hat p hat commutator. But also, I start from here with here. So that gives me, I'm going to write as minus iota I shouldn't write with minus iota, I should write with plus iota. And p hat x hat, and when I do the commutator, I get the same term with a minus sign and order reversed. So I get p hat x hat. However, this term, so m omegas cancel, and I get minus iota 1 over 2 h bar, right? And plus, same thing happens here, iota 1 over 2 h bar. But this split, I can reverse the order because a hat b hat commutator is minus b hat a hat. So I can reverse it, and they both give me the same commutator, x hat b hat. So when I reverse it, this sign gets reversed. So I get minus iota over h bar, and x hat p hat commutator is iota h bar. So this becomes 1. So a hat dagger commutator is 1. Also, you can note that if I write this a dagger a, what am I gonna get? A dagger a, they get a dagger a, this gets multiplied with this. I get x hat square m omega over 2h. Similarly, when the p terms will multiply, they will give me the starting thing. So it's the same idea which I was using in my heuristics, that why I'm trying to split it. So I'm gonna get my Hamiltonian back, but I get something extra, just like I did when I was hand waving. So what do I get an extra? This guy, because it's a dagger a, x hat p hat multiplies this, and then I get the same term but with a negative sign, p hat multiplying with x hat. So I get, well, let me see, what was it? Plus iota, m omegas cancel, plus iota over 2h bar. And x hat, p hat, commutator. So this guy is just the starting Hamiltonian. And to it, I add, this is iota h bar. So iota gives me a minus, and h bars cancel, minus half. So that means that the Hamiltonian can be written as, well, by the way, this was not Hamiltonian. Just a slight mistake. These guys were h bar over h hat over h bar omega. So I have a h bar omega over here. So Hamiltonian just becomes h bar omega a square a plus half. Now the thing is, if I find this thing, I can write like this. Over 2. If I have an operator A hat and its eigenstates, let's say I add to it a number, a constant, those are still the eigenstates. Thus the eigenenergies are shifted. Similarly, if I replace this operator by alpha A, those are still the eigenstates. Eigen values are just multiplied. So that means I can find the spectrum of these guys, whatever I get. So for example, if I have an eigen, I'm just going to call its eigenvalues n. If there is a state which is eigenstate of A dagger A with eigenvalue n, then this state will also be, because you can just check, an eigenstate of the Hamiltonian with eigenvalue n plus half. So finding the eigen values of H hat are exactly same as finding the eigenvalue of A dagger A, and it's vice versa. If you know the eigenvalues of H bar, is that directly corresponds to the eigenvalues of A dagger A. And I can just do that, and so it means whatever spectrum I get for n, I'm just shifting the scale by h bar omega, and just translating them by half h bar omega. So in other words, I'm this operator dagger A counts the energies in units of h bar omega, because I'm just shifting the scale, multiplying the difference between them by h bar omega. So it counts the energy in units of h bar omega. And since you are shifting all the states by the same constant, half h bar omega, so it doesn't matter much. The differences will still be same. In any case, let's try to see what can we do about this operator, and let me give it a name. Let me call it n and give it a weird name for now. It's called the number operator. And I'm going to look for trying to solve its eigenvalue problem, calling its eigenvalues as n. These are the eigenstates labeled by the eigenvalues. And notice the following. That these commutators, so what is this commutator? This is A with A dagger A. And since I had computed the commutator of A and A dagger in the beginning, I can use that to compute all these. So the commutator acts like a derivative. So this A, you can prove this property very, very easily. If you have A, B, C, you should have proven it in the beginning. There are lots of such properties to prove in the first chapter. Very easy to prove. You just have to open this commutator and rearrange time. So it acts like a derivative commutator. That means it first derivates this guy, B. So it's like A is derivating a product of two functions. So it first derivates B and leaves the C, and you have to keep the order. Leaves the C as it is, Then it derivates the C. So B comes first because you're keeping the order like this. So if I do it over here, I get A dagger, A plus A dagger comes outside, and A with A. So this is obviously 0 with itself. A dagger is 1. So this is A. That means A commutator with n hat is A. While if I do the same thing with A dagger, so that gives me A dagger with A dagger, A outside, plus A dagger comes here, A dagger derivates A. So this is 0. And since it's the reverse order, so this is minus 1. So A dagger n is minus A dagger. So these two properties, like these simple commutation relations which these A's have with the number operator, and we have gotten this just by splitting the Hamiltonian and rescaling. They become very useful in trying to find the spectrum. Because of these relations, we call these A, well, it will become, let me just first do something and it will become clear. Consider that you have a state, eigenstate, n to be any arbitrary eigenstate of n, the number operator. Then if I act with a hat on this state, I'll get something new. You can check that it's still an eigenstate of a number operator because it's still an eigenstate. Because you can explicitly check. I take the state and act on it with the number operator. Now I don't know what this a hat on n gives me, but I know what n hat on n on this state n gives me. So I reverse the order using a commutator. So I write n hat a hat, subtract and add the reversed order. Now I know how this guy gonna act. So I collect them and call them. Not call them, they form this commutator. This commutator I just computed above is minus a because an is a, so na is minus a if you reverse the order. So this gives me minus a hat plus a hat n hat acting on n. When this acts on it, it picks up an n, a number. So this is equal to n minus 1 a hat n. So it's showing me that a hat n is an eigenstate with eigenvalue n minus 1. So I can write it something like this. However, suppose this n was a normalized state, normalized eigenstate. So what I have learned is that if I have an eigenstate with eigenvalue n, then I also have an eigenstate with an eigenvalue n minus 1. So and call n minus 1 to be normalized, to be a normalized eigenstate with eigenvalue n minus 1, then I have no guarantee that when I act with a hat, this state which I get, all it tells me that this state is an eigenstate with eigenvalue n minus 1. But any eigenstate, if you multiply with a constant, with any constant, any number, it still remains an eigenstate. So I don't know which one is it. So I have no guarantee that this state which I get by acting with a hat is a normalized eigenstate. Then I must write that there's a possibility that there will be some constant involved, where this is normalized, right? So let me know if there is some confusion about it. When you act with an a hat on a normalized state with eigenvalue n, all you can say is that you will get a state which will be an eigenstate with eigenvalue n minus 1, which this is, assuming that this state is normalized. I don't know if there's a constant involved or not, if it's exactly the normalized state or if there is some extra constant in front of it. So I must include it. That's the only conclusion I can draw from that equation. Uh, there may be an other.
Sir,
Uh,
sir, मतलब कि हम CN को इसलिए include कर रहे हैं that if we are not sure that it would be normalized.
yeah, we have no reason to conclude that it will be normalized, because all we have concluded is that when a hat acts on n, it gives us a state which is an eigenstate of the
Hmm.
number operator with eigenvalue n minus 1. So all these states, if I call this state to be an eigenstate of number operator with eigenvalue n minus 1 and normalized, then all these states are also eigenstates with eigenvalues with eigenvalue n minus 1, but they're not normalized. They don't have to be normalized. So which one? All I concluded is that I'll get a state which has an eigenvalue n minus 1. So which one I get? This one or this one with any alpha? So I get some from this, because there's a whole way of states where you multiply one by a one-dimensional way of states, where you multiply with arbitrary complex constant and you still get an eigenstate. So it's one of those. Which one we don't know. So that's why I'm writing Cn in front, because I'm assuming that when I write this symbol over here, I have reserved for the normalized eigenstate. So I'm not sure if I'll get the normalized eigenstate, so I must include a constant. Uh, there may be another issue over here. What is that issue? The issue is that we know that sometimes we have more than one state. with more than one linearly independent state with the same eigenvalue. So suppose if you had n minus 1 A and n minus 1 B, and they are linearly independent. If you had two linearly independent states, you can generalize it to even more, and both having eigenvalue n minus 1, then if I make an arbitrary linear combination of these two, this will still be some state, let me call it n minus 1 tilde. This is still an eigenstate with eigenvalue n minus 1. So how do I know that there aren't two states or three states or let's say m states with eigenvalue n minus 1? If there are, then I shouldn't write it as one state, one normalized state. Well, even if it's one normalized state, it would be some linear combination of many linearly independent states. Maybe it is, but my claim is that it's not. It's just one state, and which is and you do not have any degeneracy involved. You do not have two states which are linearly independent and both having the same eigenvalue n minus 1. There's only one state with eigenvalue n minus 1. One state up to a constant, because whenever you have an eigenstate, it's at least forming one-dimensional subspace. I'm saying it's not having a two or higher dimensional subspace. So how do I know it? Well, actually, you can prove this little theorem. If you have, well, let's write it this way. There is no degeneracy in energy in one-dimensional bound states. So we argued last time that one in the bound states, well, that result is true even if you are not in one dimension. They always have discrete energy eigenvalues. This is some other statement. This is saying that those discrete energy eigenvalues, they will have only one state associated with them, only one linearly independent state. You have no degeneracy. So how do you prove it? It's kind of very easy. But this holds true only in one dimension. Because if it held true in all dimensions, then all bound states uh, will have no degeneracy. But actually, as you go in higher dimensions, the degeneracy is the most common situation. But in one dimension, it's not there. And we are considering a one-dimensional system. So does the proof goes on? So suppose you have any potential, any system with a potential V. Systems are characterized, one-dimensional systems are characterized by giving a potential V. And suppose there are two linearly independent states, psi1 and psi2, with same energy eigenvalue E, then being the energy eigenstates of energy means that they satisfy this equation. So it's just the Hamiltonian acting in the position basis. This is true for the first state and also true for the second one. Because they both have same eigenvalue E. Now I can multiply this by psi 2 and multiply this on the left. Well, let me write it. Psi 2 and multiply this with psi 1 and subtract. So these guys will go away because I just have a product of functions. Similarly, over here, I have just a product of functions. So they go away as well. And I'm left with psi 1 d2 psi 2 over dx square minus psi 2 d psi 1 over dx square is equal to 0. This I can write as d by dx psi 1 d psi 2 over dx minus psi 2 d psi 1 over dx is equal to 0. Because when I take the derivative, when this hits this, it gives me this term back. But when it hits this, that single derivative terms, they cancel between those two because of this relative negative sign. So this is, they are same. And this step I can do, from here I can conclude d psi 1 over dx is 0, is a constant. Now I bring in the assumption that these are bound state energies. So for bound states, we know that psi 1, psi 2 go to 0 as x goes to plus or minus infinity. So I can just evaluate this constant. Because it's a constant, it doesn't depend on the position. I can evaluate by putting any value of x in these. So I put the value at far, far away at infinity. And psi 1 it has to be 0, psi 2 has to be 0. So that means the constant has to be 0. So if the constant is 0, that means psi 1 d psi 2 by dx. So this becomes a very easy equation to solve. Is equal to uh, so I can wait. D D psi. Yeah, from here I can conclude. First, I can conclude psi 1 d psi 2 is psi 2 d psi 1, and that gives me d psi 2 over psi 2 is equal to d psi 1 over psi 1. And this gives me log of psi 2 is log of psi 1 plus a constant d. And that gives me psi 2 is equal to ed psi 1. Right? So that, what does this mean? This implies that psi 2 is a constant times psi 1. So that means psi 2 is in same one-dimensional linear space as psi 1. So psi 2 is a multiple of psi 1. They're not linearly independent. We assume that they are linearly independent, but they are not. So since they were arbitrary, so you pick any two functions which have the eigenvalue or same eigenvalue e, then they will be multiple of each other. So that means there is no degeneracy. And one dimension was crucial in concluding all of this. None of this manipulation, like coming from here to here, from here to here, if you had a Laplacian sitting over here, you won't be able to conclude any of this, any of this. So works only in one dimension. And to put this constant equal to 0, we had to use the bound state. But the conclusion is that there is no degeneracy. If you get one eigenstate with energy E, all the others are just a multiple of it. No other, no linearly independent one. So that means I don't have to worry about anything like that. This is all I need to write. Because if n minus 1 is an eigenvalue, there's going to be only one dimensional space. So all states will be multiple of this one normalized eigenstate. And I have whatever number is generated by this operator, because this operator has a specific operation on this state. I only know that this is going to give me the eigenstate with eigenenergy n minus 1, but with what constant, I don't know. I haven't computed yet. So I just write it as Cn. So any question?
No,
Any?
sir.
Now, what I do, I can also check this. If I have a state, again, I take this state n and check a dagger n. Turns out this is also an eigenstate, because when I act with this guy on this, what do I get? I can again add so I can combine these two to give me this guy. Now a dagger n commutator was -1. So n a dagger commutator is +1. Uh, uh, well, I had a dagger n is equal to minus a dagger. So n a dagger is plus a dagger. So I get a dagger, and when n acts on this, it picks up an n. So I get n plus 1 a dagger n. So a dagger n is also an eigenstate with eigenvalue. So this implies if n is an eigenvalue, so is n minus 1. And if I call, sorry, n plus 1. N minus 1 we have already proved that n minus 1 is also an eigenvalue and n plus 1 is also an eigenvalue. And if I call n plus 1 to be the normalized state, when I say D, I still have the freedom of phase, but I'm just absorbing it. I'm just choosing some phase, let's say one phase, which just gives me one. If I call n plus 1 to be the normalized state, then this means that a dagger acting on n gives me a multiple of this normalized state. And let's call it some other constant, call it Cn plus 1. So what we have proved is that if there is any eigenstate of the number operator with eigenvalue n, then I'll find an eigenstate with eigenvalue n minus 1, and I'll also find an eigenstate with eigenvalue n plus 1. So if I have found the eigenvalue n minus 1, then by the same logic, this is an eigenstate. I can find an eigenvalue n minus 2 by acting with A. All I have to do is take this, act with A, I'll get an eigenstate with eigenvalue n minus 2. I'm guaranteed with some constant Cn minus 1. Similarly, I can act on n minus 2. I'll get n minus 3. So on and so forth. Similarly, I can go in the other direction. This is an eigenstate with eigenvalue n plus 1. And the same logic tells me that n was nothing special. You start with any eigenvalue, act with a dagger, you get 1 added to your eigenvalue. So I'll start from n, I'll have this whole tower in both directions. So it goes up to, it changes, this tower changes with 1 at each step in both directions. So it seems like it goes to infinity above and minus infinity above. However, my claim is that it cannot keep going downwards because that would be a contradiction to another theorem. Because remember that these eigenvalues of this number operator, they are proportional to the eigenvalues of the Hamiltonian. They are proportional to eigenvalues of Hamiltonian because these all states are also giving me eigenvalues of Hamiltonian. Just multiply this number by h bar omega and add a half. Add a half to any eigenvalue and multiply by h bar omega, and that would be an eigenvalue for the Hamiltonian. So the n can keep going to any value downwards, then the Hamiltonian will also have any value, any negative value down there. However, my claim is that the eigenvalues of this Hamiltonian are all non-negative. How do I know it? well claim proof. If I compute the average value of energy in any state, in any arbitrary state, this is what? I just sandwich that state between this operator. Sandwich this operator between that state. That's how you compute the average value. So I get this. And because of the quadratic nature, this becomes a non-negative operator. Because the operators are coming as squares, that essentially gives me this result. Because it's a Hermitian operator. So it can act this way and it can act this way. So I can write them as P acting on psi, whatever state I get. Right? Because P acts both ways. And X acting on psi. Now, by the starting postulate of vector space, this is more than 0, equal or more than 0. Similarly, this is equal or more than 0, because the scalar part of a vector with itself is real and it's non-zero. So that means this is a positive number. This is positive. So this whole thing, and there's a plus sign in between. So no worries, is equal or greater than 0. Now I can take this result is true for any state. If I take any eigenstate of H for this computation, let's say E, psi is chosen to be an eigenstate, then this result tells me that this is greater than 0, but this is an eigenstate, so it picks out E. This is positive, again by the same argument, so E is greater than or equal to 0. So I cannot have an eigenvalue of the Hamiltonian which is less than 0. But the eigenvalues of the Hamiltonian, but this I just found out this is an eigenvalue for any n. So this has to be greater than 0. So that means n plus half has to be greater than 0, or n has to be greater than minus half. N cannot be less than minus half. So that means, how can this be? I just concluded that if I start with any eigenstate, I can start applying A and keep going down. By the way, that's why they are given a very specific name, because A is bring you to a lower eigenvalue. A is called the lowering operator. And A dagger, since it takes you up, is called the raising operator. So how can this be? On one hand, I just proved that you cannot go lower than minus half. starting from any arbitrary number n. While this is saying that you can keep going as much as you like. Well, this lowering can stop. I will not have contradiction with this equation. So what does this lowering told me over here? That there is, when I apply a hat on an eigenstate, I get a lower state with something multiplied with Cn. So this lowering can stop if at some point I get a zero over here, because that would be completely consistent, because this thing, if this is zero, then all I have to have is equal to n minus 1 times 0, which is true. 0, when you get a 0 vector, that's not, when you get a 0, that's not an eigenvector. So that means this lowering has to stop. There is, as you go down n to n minus 1 to n minus 2, you go to some, you come down to some number n naught, such that when you act, this is the lowest possible number, when you act with n naught with a on it, you must get a 0. But from here, I can multiply with a dagger on both sides. 0 just absorbs everything. It's still 0. What is this guy? This is the number operator. Sorry, this is the special, this was the special one. So this is number operator, and this was an eigenstate, n naught. This was the last eigenstate, below which I get a 0. So this last eigenstate in this chain, this state is not 0 because this exists. Below it, you get a 0. So how can this equation be satisfied? This implies that n naught is 0. So this last eigenstate has eigenvalue 0. So that means if I start from any n, I will come down always to an eigenvalue 0. But I was coming down in integer steps, and I landed on 0. That means every step in between was integer. This implies that the starting n number, n must be a positive integer. There's no other way. So, and you can think in terms that this is the lowest 0. So when I apply a dagger, I go up in integers. So I go from 0 to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So we have found a whole tower of eigenvalues of the number operator, and which consists of, it starts from 0 and goes up in integer steps all the way to infinity.
Sir,
जी
सर थोड़ा सा आउट ऑफ टॉपिक सवाल है, लेकिन ये जो हमारे एनर्जी लेवल्स हैं, दे आर लाइक द सेम जैसे वैलेंस शेल होते थे जब हम केमिस्ट्री में एटम पढ़ते थे, मतलब आर दे कनेक्टेड और
Well, they were the valence, they were the energy levels if you have a Hamiltonian, which is described by a Coulomb potential.
तो are they connected मतलब ये
Yeah,
उसी
that's
तरह
the
की
same thing. That's what I'm saying. Energy levels of a Hamiltonian whose potential is a Coulomb level. They will not have this form, these integer going up. As you know that they have a very different form. They have the Bohr levels, but they are same. I mean, K is the same concept. You're just solving for the eigenvalue equation for the Hamiltonian. In this case, it's the one-dimensional harmonic oscillator. In that case, it's a three-dimensional Coulomb potential. But you get a spectrum because it's also you're considering the bound states in that Hamiltonian. So those bound states turn out to be discrete, quantized, and then your job is to find that what are those allowed values, what are those allowed energies. And in that case, actually, what you get is that not only you can solve, you can get the exact energies in case of hydrogen atom when you have only one electron. So you have just a two body problem. So just one potential for one coordinate. You can get all the bound state energy values, and you also find that they are degenerate in that case. So you can also compute that each eigenvalue, what are its degeneracies, and you can compute the exact states as well. Like we will compute the exact states in this case, but we will do that as well later on. And why did you ask this question? I'm like really mad now.
सर वो जब भी आप पढ़ाते थे तो मेरे दिमाग में वही क्योंकि वो when मतलब when it goes from one valence shell to another तो वो energy या तो release होती थी या absorb होती
Yeah,
थी
that's
तो
exactly
ये
what that's exactly what it is. If your this oscillator is in this state, if it has to come down, if it has to change the state, its energy is changing. So the energy has to come out somewhere. Or if you want to take it from here to this level, you have to provide this energy difference. So in case of atomic systems, or even if you consider this electron to be this system to be an electron trapped in some kind of a harmonic oscillator, if you have to take it up, the best way to manipulate an electron is through a photon. So you have to provide it a photon of exactly this energy, this difference. Not any arbitrary photon will do the job because there are no states in between. You have to take a jump between these levels only. So that's why the photons which will be absorbed or photons which will be released if it changes these levels will have very specific energies. And because this is true for photons, it will have very specific frequencies. So that's how you experimentally test these things, test these levels. You can check if these levels are have exactly these values by computing the differences, by looking at the frequency of the lights, of the possible light coming out of it. That's how you get that line spectra. You may have heard that if you pass the light coming from a particular atom, it doesn't have all the frequencies. Or if you shine a white light to some diffused atoms of a gas, it absorbs some of it, but it doesn't absorb all of it, all frequencies. It absorbs very specific frequencies, which are called the line spectrum of that particular gas or that particular atom. So those lines correspond to these jumps. And that's how we know, because of these lines, we know that the possible energies inside the atom are not arbitrary. They are quantized. They have very specific energies. So the issue is like I'm not uh, giving a complete introduction of physics, like these normal, these usual things, that how the quantum mechanics. Well, these were the observations which forced people to consider quantum mechanics. But since we are not discussing the physics much, we are more interested in the theory itself. So I can't spend much time discussing those things. But there was a nice mathematical argument which was going on that has been derailed. In any case, so we got this, that n must be a positive integer, and and this is true only for harmonic oscillator, that this particular spectrum which we are finding out. N is a is a positive integer, and we have found a tower of possible eigenstates of the number operator. They start from 0, and then you have just integer values. That's why it's called the number operator, because its eigenvalues are just the natural numbers. Now, you can ask, I've got one tower, is there another tower? Maybe I started with n. What if I start with n dash? Maybe there's another eigenvalue n dash. Eigenvalue n dash in spectrum. And from this n dash, but if this eigenvalue is there, again using the same arguments, I can start coming down. So on. And again, I'll find that there's a lowest lying state defined by this. But the same conclusion will hold, that this eigenvalue is 0. So that means there will be this lowest lying state would be 0. And when I go up in steps, I again get 1, 2, 3. So even if there's, so that means this n dash, which I chose, also was an integer, is also an integer. This was kind of clear once I proved that you start with any eigenvalue, you come down in unit steps, you hit the 0. So no matter which number you start from, that number is forced to be an integer. There's no other possibility. So that means if I have these two towers, the towers match. But I just proved in the theorem in the beginning that there is no degeneracy. So this state has to be then a multiple of this state. I do not have two states with the same eigenvalue. So I don't have two towers. There's just only one tower. And these are all the eigenvalues. There are no other eigenvalues. All eigenvalues of n are 0, 1, 2, 3. Because if I assume that there's another eigenvalue, I hit the 0. I always hit the 0. So the eigenvalues are forced to be integers because of that fact. So these are all the eigenvalues, and this implies all the eigenvalues of H Hamiltonian are H bar omega n plus half, where n is 0, 1, 2, 3. So the minimum energy of oscillator is equal to half h bar omega. This is sometimes called minimum 0 point energy. So like a classical oscillator, its minimum energy is sitting at the bottom, while a quantum oscillator always has a minimum energy. So you can say it's always oscillating in some sense with some minimum amount given, which gives it this much energy. And that should be like that. You can argue from uncertainty principle because if it had zero energy, that would mean that it had to sit, will have to sit at the zero of the potential. This has to be zero because it's half m omega x square. If this is zero, that means x is zero. And it will have to have zero kinetic energy. That would mean that P is zero. But that means in that state you would know that momentum and position both are known exactly. But that's not possible. You can't be sure about both momentum and position. That's against uncertainty relation. So it can be staying still over here. There is some uncertainty in position and some uncertainty in momentum. And that gives it a 0 point energy. Um, Now we can also find these. So we have solved this eigenvalue problem. We have found all the eigenenergies. This part is done, but we need to also find the eigenstates, because if we want to compute time evolution, or if we want to describe the system completely, we will be expanding it in the eigenstates of the Hamiltonian. We can leave it like symbolically. So the eigenstates are these, symbolically like that. But if you want to compute some other probabilities, like the position probabilities in these states, momentum probabilities, so we will have to project them onto position and momentum basis. So we will need to know that form as well. Should we stop here, or should we do a little bit more?
सर हम जवाब दें?
हाँ, तो और किसने देना?
सर मैं तो यही कहूंगी ना, बस अगले हफ्ते पढ़ाइएगा बात।
अगले हफ्ते नहीं, कल।
कल नहीं सर,
चले।